Today I'll be presenting Lab 4 on oscillations. In this experiment, we studied the motion of a spring mass system. However, instead of just moving straight up and down, the mass oscillates in an arc, which makes the motion slightly more complex and more realistic compared to idealized examples. This lab focuses not just on observing motion, but also on connecting that motion to fundamental physics principles. The main purpose of this lab was to investigate how a spring mass system behaves and determine whether a computational model of that system follows the energy principle. To do this, we use two important tools. The first tool is Tracker, which is a video analysis software that allows us to track the position of an object frame by frame. This gave us real experimental data for how the system moves over time. The second tool was GlowScript, which we used to create a computational model. This model simulates the system's motion and calculates how its energy changes as it oscillates. The goal is to compare these two approaches, the real-world data and the simulation, and see if they agree. More specifically, we wanted to check whether total energy stays constant, which would confirm that the energy principle is being followed. In the end, our results show that the total energy remained essentially constant, supporting the idea that energy is conserved in this system. To understand what's happening in the system, we relied on two key physics concepts, being Newton's second law and the energy principle. Newton's second law tells us that the net force acting on an object determines how its motion changes. And in equation form, it relates force to the rate of change of a momentum, and this is what allows us to predict how the mass will accelerate as the spring pulls on it. And then the energy principle, on the other hand, focuses on energy instead of force, and it states that the change in the system's total energy is equal to the work done by the system, or on the system, plus any thermal energy transferred. In an ideal situation where no energy is lost to the surroundings, the total energy of the system should remain constant. In this lab, we used both these ideas together. Newton's second law helped us build the equations for motion, while the energy principle helped us evaluate whether our model was physically accurate. For the experimental part of the lab, we used Tracker to analyze the motion of the mass. The mass of the object was about 0.402 kilograms, and the length of the system was about 0.7 meters. The object started at a specific initial position and had an initial velocity of 0, meaning it was released from rest. By tracking the object frame by frame, we were able to record its position over time, and from this data, we calculated several important values. One key value was the period of oscillation, which tells us how long it takes for the system to complete one full cycle of motion. We also calculated the spring stiffness, which indicates how strong the spring force is, and the relaxed length of the spring, which is its natural length when no forces are acting on it. These values are important because they allow us to accurately describe the system and use realistic parameters when building our computational model. After collecting experimental data, we built a computational model using GlowScript. This model simulates the motion of the spring mass system by applying the forces we derived from Newton's second law. At each time step, the program calculates the net force on the mass, updates its velocity, and then updates its position. In addition to motion, the model also tracks energy. Specifically, it calculates kinetic energy, which depends on how fast the mass is moving, and potential energy, which is stored in the spring when it is stretched or compressed. As the system oscillates, energy is continuously transferred between these two forms. For example, when the mass moves fastest, kinetic energy is at its maximum, and when the spring is most stretched, potential energy is at its maximum. By graphing these energies over time, we can clearly see this exchange happening, which helps us better understand the system's behavior. So although our results were generally consistent, there are a few sources of error that could affect the accuracy of the experiment. One major limitation is that the system is not perfectly isolated. External forces such as air resistance or slight friction at the pivot point can remove small amounts of energy from the system. And then another possible source of error comes from using Tracker. If the center of mass is not identified precisely in every frame, it can introduce small errors in the position data. There may also be small measurement inaccuracies in values like length or mass, which can affect calculations such as spring stiffness. Even though these errors are relatively minor, they can still cause slight differences between the experimental data and the computational model. So to determine whether the energy principle is satisfied, we analyze the total energy of the system in our computational model. The results show that the total energy remained essentially constant throughout the motion. While kinetic and potential energy were constantly changing and transferring back and forth, their sum did not significantly increase or decrease. And then this indicates that there were no major external forces doing work on the system and that energy was conserved. Because of this, we can conclude that the computational model successfully follows the energy principle and accurately represents the physical system. So in conclusion, this lab demonstrated that a computational model can accurately represent the motion of a spring mass system. By combining experimental data with simulation, we were able to confirm that energy is conserved, which aligns with fundamental physics principles. Thank you for listening.